Hello, everyone. Welcome to the second webinar in the joint Tran-SET Webinar Series, which covers a pretty wide range of topics related to transportation infrastructure resilience to extreme weather events. My name is Chris Malson. I'm the Program Manager of Tran-SET, which is Region 6's University Transportation Center. And this webinar is jointly hosted by us, by Tran-SET, and also by Region 2's UTC, the University Transportation Research Center, which is led by the City College of New York. So yes, please feel free to visit both of our websites. Tran-SET has, all the funded research that they sponsor on their website. We also have a quarterly newsletter that you can subscribe to, as well as an email notification list. So again, I encourage you to at least visit our website and peruse the research that we sponsor. So today we'll have 4 20-minute presentations, and we will save the questions till the end of all 4 presentations. There is a Q&A box where you can type in your questions, and then you can do that throughout the entire webinar. And at the end, I will have a 10 to 15-minute Q&A, which I'll take the questions from that Q&A box. And if there's no Q&A, we can also, questions in that Q&A box, we can probably open up the lines too if you want to ask a question directly. Without further ado, I think I'll introduce our first speaker, Dr. John Miller. Dr. Miller is a Research Associate Professor of Coastal Engineering in the Department of Civil, Environmental, and Ocean Engineering at Stevens Institute of Technology. Dr. Miller received his bachelor's degree in civil engineering from Stevens in 1999 and a master's and PhD in coastal engineering from the University of Florida in 2001 and 2004, respectively. While at Florida, Dr. Miller received a Fulbright postdoctoral fellowship to study at the University of Queensland in Brisbane, Australia. Dr. Miller currently serves as the New Jersey Sea Grant Coastal Processes Specialist and Director of the New Jersey Coastal Protection Technical Assistance Service.
Well, thank you for that introduction. And what I'm going to be talking to you about today is actually the result of many years of work by many. It's been performed by many colleagues, PhD students, graduate students throughout the years. So although my name is on this presentation, it certainly is not the result of a singular individual effort. It's really a compilation of a lot of the things that we've been working on, and in particular, focusing on flood impacts to transportation infrastructure. So on the intro slide, you see that the picture on the right there. So Stevens is a relatively small school, for those of you, just to orient you. In the foreground of the picture, there's a tall building that's actually on Stevens campus, and we sit along the Hudson River looking out across Manhattan. So we have one of the best views, I think, in the entire world. But the Hudson River, as you see, is sort of in our backyard and in our front yard sometimes. And that relates to kind of what we're going to be talking about today, which is some of the work that Stevens has done in the area of flood forecasting, just generally speaking, but then more particularly related to the impacts on transportation infrastructure and some of the things we're doing now, and that can be, I think, useful and beneficial moving forward. So, of course, why do we do flood forecasting? Why do we care? Well, obviously, given the events of the past week, and you said past week, really the past year or years, we see that we continue to be impacted by events kind of like what you see on this slide here. I just took a snapshot, but pretty much every coastline of the U.S. is impacted by storms, coastal storms of one flavor or another. Here we have Katrina, Florence, Maria, and Hurricane Sandy. Hurricane Sandy is the one that's near and dear to our hearts up here in the Northeast, because it obviously generated a significant amount of damage, impacted us in this region in a manner which we're relatively unused to dealing with. So we know we have this issue. What does it cause in terms of impacts on transportation infrastructure? This series of pictures on this slide kind of just illustrate, just not all, certainly, but just some of the impacts that we see related to these storms. And, I selected these pictures specifically just to point out that when we say transportation, this really is intended to cover sort of, I don't say all aspects, but you see airports, you see trains, you see buses, you see cars, you see cargo containers, bridges, subway tunnels, pretty much touching on all different aspects of transportation. And obviously there are many, many impacts that go beyond transportation, but again, today mostly focusing on just transportation impacts. And of the pictures you see here, there's only one, actually, the bridge in the lower right-hand corner that does not correspond to Hurricane Sandy. So these are, you know, just examples from my personal neck of the woods up here in New York and New Jersey. So as illustrated on that previous slide and kind of also spelled out here, you know, when we talk about flooding, which is something generally we're overall concerned with here at Stevens, when we think about transportation system impacts, we think of it in a number of different ways. I think the first way that we typically think about it, and certainly the first sort of, I think, impetus for us to do our flood modeling research, has to do with actual flooding of major highways, freight and passenger rail, airports, port facilities. Again, basically stuff getting wet is kind of what's going to get wet and when is it going to get wet. Is certainly one of the aspects, but you know, another aspect which I think we haven't quite explored in as much detail, but we certainly have capabilities to, is to look at you know, what this water does in terms of structural damage potentially to any number of facilities, marine terminals, bridges and tunnels, and roadways. I think these are all areas of research which are currently ongoing, but the opportunity to take some of the flood forecasting and the advanced hydrodynamic simulations that we're doing now, and being able to translate that and scale that up to use in other types of studies, for example, studies of when bridges might fail. There's certainly more opportunity to go further than I think where we've come so far. So one of the things that is particularly important when it relates to transportation infrastructure is advanced warning. The idea that we are concerned not only with predicting how much water is going to get where, but also really the timing of that. So when is the water going to get high? This is really critical because transportation provides a mechanism or means for people to get out, to evacuate, to leave. And we need to understand, you know, when we need to begin to shut things down, when we need to make preparations, change lanes and roadways and things like that. And providing information is only useful if we have enough lead time. So if we're able to provide the information far enough in advance that people can react to it. So in dealing with some of the aftermath of Hurricane Sandy and dealing with operations and emergency managers here in New York and New Jersey, roughly 72 to 96 hours is the lead time, which is commonly specified as necessary for making critical decisions. So, as I said, we've been studying storm surge modeling or flooding here at Stevens for quite some time. After Sandy, we have kind of revived, or we have changed the way that we look at flooding, and we have developed what we call the Stevens Dynamic Overland Inundation Modeling System. It's a system that really looks at not just the water when it's out in the ocean or in the bays or in the rivers, but really what happens to the water when it starts to come onto land. So the overland inundation part is something that's pretty much new for us since Hurricane Sandy. The background that we use, or the backbone of our modeling, is based off of our New York Harbor Observation and Prediction System. This is a system that we've had in place at Stevens for a decade and a half now, so predating Sandy. It's basically a system for predicting storm surges, currents, salinities, water temperatures, etc. And it's based on a derivative of the Princeton Ocean Model. And it's an operational forecast for NOAA through the IOS program. And you'll see now here the enhancements that really we're sort of working on now and we're perfecting have to do with the overland flow, incorporating rainfall, so not just considering water coming in from the ocean or from offshore boundaries into the land, but also coming down through different watersheds and streams and tributaries and making its way into areas. And then ensembling. We'll talk a little bit about most of these. So for those of you who are really into the geeky side of this, here's just some information about the NIHOP system. Again, it's based on a shallow water version of the Princeton Ocean model, specifically called CCOM. Some information about the model there. It's actually, our hydrodynamic model is dynamically coupled with a model for predicting waves. In this case, it's a derivative of the Great Lakes model, modified specifically for our applications, including offshore boundary conditions from swell propagating into the boundary. And again, we use this model, this system, or this modeling system as sort of the backbone for everything that we do. We actually run our NIHOPS model operationally, which means that it's run basically in both storm conditions as well as just in day-to-day conditions. There's a number of inputs that go into forcing the model: tides, surges, waves, pressures, etc., rainfall, river discharge, ice, you name it. There's many inputs that we get from both sensors that we put out, but also sensors that other people are putting out, as well as forecasts put out by the National Weather Service, for example. All that information comes in, goes into the model. The model crunches all the numbers, and we output basically 96-hour forecasts multiple times per day. These forecasts consist of things like total water levels, currents, salinity, temperature, wave heights, and periods. And we've been doing this dating back since 2006. And again, this is an operational system, so it's all this information is available and served via a website, one of the Stevens websites. So again, one of the new things since Sandy is really understanding how water moves over land and potentially impacts things like transportation infrastructure. And so in order to do that, essentially we've incorporated an overland flow portion of the model. Basically requires really high resolution information related to the topography of the land on which the water is flowing over. So fortunately, we have lots of great LiDAR data sets now from which we can derive DEMs that are very high resolution. And we can use this in combination with some numerical techniques. For example, we're using depth integrated equations of motion to predict what happens to the water once it reaches that land-water interface. And based on that, we can predict water levels as well, not just water levels, but water levels as well as currents inside of model cells, which happen to be over land, or generally when there's not a storm occurring. So the model, of course, is calibrated. I think the real thing I wanted to point out here is that all of this only happens when we have can only be performed or can only be done when we have accurate data to ensure that we're actually modeling something real. So there's a lot of information, a lot of data points that come in that we can calibrate and validate too. So collection of actual real data is an important component of this. And what you see in the picture here on the right is actually one of our data collection stations. But we use, again, none of this could be done in isolation. So we are very heavily reliant on information that we collect also from NOAA, USGS, and again, the Weather Service and other organizations. All that plays an important role in us being able to do what we do. So the model has been calibrated, particularly for our Sandy calibrations. We were using the battery tide gauge in the Upper Harbor. Validation of model. So we actually took a look at our Sandy simulations, and what we did is we validated that using information obtained by the USGS, as well as actually an interesting thing. We used some crowdsourced pictures of estimating peak water level. So people went out after the storm, after Hurricane Sandy, and took pictures of where they saw water, and they have a timestamp on that. And so we were able to utilize some of that as a part of our calibration, not the entire, or part of our validation, not as an entire validation, but it was interesting to kind of incorporate that technology. We were just talking about getting on Facebook Live. Well, this is sort of an application of that social media technology. Overall, you see in the plot on the right, it's our model validation curve, which shows that overall the model works really well, which means that we can use it for a lot of interesting things. Here's an example of an application of the model to transportation infrastructure. So what you see here is actually a simulation of flooding during Hurricane Sandy. So what you see is a rail yard The movie should be running. Hopefully the video stream is working. And what you'll see on the bottom here is you have your tidal curve. So the water starts to get high on the high tide before the peak. And then you get towards the peak and the water comes in, and we can figure out what's getting wet and where. And then you'll notice the arrows are actually the current velocity vectors. So we're getting not only water surface elevations, but also velocities of water. So for example, if you have infrastructure here, you can figure out what the loads on that infrastructure might be. One of the really important things that has allowed us to go out to 96 hours is implementing ensembles. This is one of the main things that we've been working on, in addition to the overland flow. In order to be able to predict out a significant amount of time with confidence, we needed to improve the way that we were. Originally, the NIHAPS model was a single model based on a best forecast. But more and more, when we looked at it, we realized that there's all these different ensembles being done, performed for weather modeling, that we needed to adopt a similar technique for our hydrodynamic modeling. So essentially, we've adopted this ensemble approach where we've incorporated, we look at 125 different weather models. So with Hurricane Florence, you just saw the cones and the uncertainty and the spaghetti models. Well, basically, we're taking all that information, plugging it into our hydrodynamic model to get our estimation of where we think the water, how high we think the water is going to get, and what types of forces that water might have with it. So we run a number of different ensembles, which allow us to create both our best forecast, which you see is the pink line in this graph here on the right, but then also a range of uncertainty. So the gray basically represents uncertainty and variability, and we're reasonably certain there's 95% confidence interval there. So we're pretty certain that the observations will fall within that. This allows us to both provide information in terms of what we think is going to happen, but also sort of what we think might be the worst case scenario, and also potentially the best case scenario. And we do all this out 96 hours. This is just another example of that application to the rail yard that you saw in the previous video. And this is the type of thing that we can do with this information. And this graphic is actually courtesy of BEM Environmental Systems. We had worked with them on a project with New Jersey Transit, looking at how do we translate the information that we provide, how do we make it understandable for decision makers. And so that's BEM came in and created this great graphic which took our information and essentially showed New Jersey Transit what was going to get wet, at what point it would get wet, and again, with the information that we provide, we can also consider, what's the most likely, but also, what in the worst case scenario. So this has been a very useful project for us. We can also predict the timing. So, for example, at a facility like this, at what point do we need to think about shutting off power to certain portions of the rail yard? Well, we have estimates of, at this hour, we expect, these tracks to be inundated, and, a couple hours later, a different set of tracks potentially. So far, everything that we've sort of talked about has been sort of on the operational side. We not only can utilize the information from the type of modeling that we're doing on sort of the operations. So again, the previous example, if you own that rail yard, you can figure out what precautions you need to take, where you might have to move your trains, et cetera. That's certainly one application of what we do. But with this tool that we have, we can also begin to look at applications to planning and or design, which is through running different types of simulations. So this slide just kind of gives an example. We can do different types of scenario building exercises. One of the things that one of our researchers, Dr. Orton, has worked on extensively is taking the models that we have and applying them to sort of long-term, long-range climate type scenarios or situations. Allows us to sort of explore different, potential sea level rise scenarios. What happens if we add, the current trend? What happens if we look at the worst case sea level rise? How is that going to impact some of the values that we see, both again in terms of flood heights, but also potentially currents and forces, currents, waves, et cetera, that we see. Actually, the publication on the right-hand side was something that we had worked with him on, where he looked at he considered a climatology of 600 plus storm events, looking at a number of different hurricanes, both real and synthetic events, and did a really extensive analysis looking at the flood hazard in New York Harbor. And we can now do this with the types of models that we're working with, and provide information that potentially might be useful not only for planning purposes, where to put certain things, but also in terms of design. So what is the, what's the current going to look like moving past a certain building in a very unlikely but severe storm event. Same thing with waves and things like that. I'm already at my conclusions. Basically, hopefully, what I've kind of tried to show here is that there's a lot of really interesting work that we've obviously focused on the work that Stevens has been doing here, but in addition to Stevens, there's others working on other groups working on similar types of aspects. But really, we've come very far in the past decade in terms of being able to use advanced high-resolution hydrodynamic models, and that advancement has allowed us to do things both on the operational side in terms of providing relevant, accurate information for decision makers and the emergency management aspects, providing flood forecasts 96 hours in advance. One of the main tools that has allowed us to go out that far again with certainty or with accuracy is the ability to do these types of ensemble modeling approaches. We didn't really talk about it, but the ensemble modeling approaches require significant computational power. But nowadays, with supercomputers and clusters, this is becoming less of a limitation. So we're beginning to move in that direction more and more. Another thing that the ensembling approach allows us to do is to provide estimates of uncertainty. So again, the gray envelopes that you saw in some of those plots gives us an estimate of the maximum and minimum water levels that we potentially expect to see during storms. And that uncertainty can be, again, very important to decision makers, but also on a design side as well. The models such as the NIHOPS model, the operational version that we're using here, they are being used. But again, one of the things I'd like to point out is I think that in many cases we're only scratching the surface. Again, most of the work that we've done so far here at Stevens has focused on prediction of water levels for sort of emergency management applications. However, there's a whole host of other information that comes along with that in a model like the ones that we run. That information being current speeds, potentially wave heights, water temperatures, water quality parameters. So thinking outside of the transportation side, but if you want to think on the ecosystem side, so we can provide information that's there. So really, we're looking to see moving forward in the next couple of years how we can kind of push some of these other applications of these types of models. And I think that's pretty much all I had. I did want to certainly acknowledge, again, some of our funding sources, because this project has, again, taken place and has been built over literally a decade and a half. I could fill up the entire slide with agencies which have supported the effort in various ways throughout the years. Most recently, after Sandy, we've gotten some funding from the agencies you see on the bottom here that really helped us kind of push the envelope and have taken us well beyond where we were to kind of, the great things that we're able to do today. And certainly, of course, want to thank some of our current and former colleagues that have contributed significantly to the development of this model over the past 15 years or so. And I think that's all I had.
Thank you very much, Dr. Miller. So the next, and again, I want to encourage, first of all, thank everyone for using the Q&A box. We're getting several questions, so that's awesome. And again, we'll get to the questions at the end of the four presentation. I'll introduce our next speaker, which is a Tran-SET funded and sponsored research project. Dr. Adolfo Matamoros is a professor in the Department of Civil and Environmental Engineering at the University of Texas at San Antonio, where he joined the faculty in 2014. He previously worked at the University of Kansas for 15 years, where he held the titles of professor, associate chair for undergraduate studies, and director of laboratories. He received his MS and PhD degrees in civil engineering from the University of Illinois at Urbana-Champaign and the degree of Licenciado from the University of Costa Rica. His research interests include behavior of reinforced concrete structures under extreme events, high-strength concrete, seismic evaluation of older reinforced concrete buildings, shear strength of reinforced concrete in pre-stressed members, and fatigue and fractures of steel bridges.
Okay, thank you. First of all, I'd like to recognize the support that Tran-SET has given us, and this is very significant. I think we're trying to develop a new direction here in the research program that I think is very useful. And when you compare the amount of risk and damage that we incurred due to hurricanes with the amount of money that we're investing in trying to learn how to prevent it. We all know the outcome of Hurricane Katrina. It cost a lot of money in terms of damage to infrastructure in Mississippi and Florida, and the repair in the aftermath was very significant. And so the impetus of our research program is to learn about the hydrodynamic problem so that we can get a better understanding on how to design our bridge structures to be more resilient. So if we think about the hydrodynamic response of bridge structures, there are two factors that affect it. There's certainly the characteristics of the waves, the height of the storm surge, and the dynamic characteristics of the wave themselves, wave amplitude, wavelength, and there are others. Didn't want to crowd the screen to make a full comprehensive list. And on the other side, there's the characteristics of the bridge. We talk about the types of connections that are used, the flexibility of the substructure, the geometric configuration of the bridge. And because in civil engineering, we have historically tended to work in silos and bins that are separate from one another, a lot of our research resembled that division between the light blue and the light orange. Folks in the water resources area and hydraulics have done a lot of work related to understanding waves and their characteristics and the type of pressures, if you wish, that they generate on bridge structures. And then there's sort of a dividing line and a gap there, and the structures people maybe come up with some equations to quantify those demands and design the structures appropriately. What we're trying to do is to bring the two together and take advantage of newer methods that will allow us to approach the problem in an integral way, where we consider not only what the waves are doing and what the bridge does, but as the bridge deforms, that affects and that informs the behavior of the fluid, and the two have an interaction that until now I think has not been investigated very carefully. So there are certainly several types of actions that are generated when a hurricane impacts a structure. The ones that come up more prominently due to dynamic effects of wave impact are a drag force and an uplift force. And those can be accompanied by an overturning moment. And these are equations, for example, that were proposed by Douglas et al. In 2006. And you see a lot of coefficients, C sub R, C sub H. Those are empirical coefficients that we really don't have a good handle on. A lot of the research in the area of fluid structure interaction comes from oil platforms, because that was an area of economic need and development. And the geometric characteristics of our structures are significantly different. And you'll see parameters there also that have to do with the storm surge. So if the storm surge is high enough, you can get into situations where where the buoyancy forces, if the bridge is not anchored properly, may be enough to lift the bridge. But even if the storm surge is not high enough, the dynamic effect of the waves may be enough to cause unseating of the bridge, like we saw in the pictures that I presented earlier. So here's a simulation, and you know, those of you who are familiar with bridge construction and the Texas Louisiana codes would be prompt to say, well, that's not the type of bridges that we use. But we sort of like this simulation because the flat edges of the bridge make the computational cost a lot more reasonable. And this is a simulation where we've gone and put a substructure with shear keys, and it sort of illustrates in a qualitative way what can happen due to this dynamic effect of the bridge, of the wave impacting the bridge, where you see if the uplift force is high enough and the structure is not properly anchored, then we can end up in a situation where we have unseating. And so also reading the reports from Hurricane Katrina, we found a lot of different types of connections. There were instances in which the bridges were simply placed on top of the piers. There were instances in which the bridges were actually anchored with some reinforcement to the piers. And so there were instances and there were shear keys. And there was damage in all of these. And so it's impetus of our project is to try to understand a little bit better the magnitude of those forces for different ranges of wave characteristics, so we can understand how to design the connections better. One of the problems also is that waves impacting on a bridge are an impact problem, not unlike entirely. There's some similarities between what happens then and what you have in a blast type situation, where you get a very sudden force that comes from the wave impact, and then there's a dynamic response that follows. And so that has different implications for the bridge superstructure than it does for the connections. And those of you who might have designed precast panels to blast loads would be sensitive to the fact that those connections between the panels and the building are a real area of concern. Well, the same thing happens in bridges, and we don't understand very well how that evolves and what type of damage can we expect for different types of connections. And so one of the areas where there have been helpful developments in computational mechanics is we're beginning to see in the mainstream multi-physics models that we can use for simulating fluid structure interaction problems. Also, they're becoming more common, the presence of clusters and supercomputers. We can then attack problems that are larger in scale. That's also helping. And ultimately, what we're trying to do is to use those methods and that additional computational resources that have become available in the present to develop fragility relationships where we understand or we quantify in some fashion the probability of damage that bridge structures incur during hurricanes. So two of the common or more recent types of methods that we see in the literature in computational mechanics are couple Eulerian Lagrangian methods or smooth particle hydrodynamics. So we, when we started with this project, we evaluated the possibility of using both methods. I think the development of smooth particle hydrodynamics is very promising, but it lags. It's a little bit further behind. So we settle in the use of coupled Eulerian Lagrangian approaches. They're more mature, and I think they're easier to implement with the technology that we have available to us right now. And in these couple Eulerian-Lagrangian methodologies, we use Lagrangian methods, that means traditional finite element type analyses to model the solids. And in that case, we're solving equilibrium equations of structures that we can simulate as three-dimensional brick elements. In the case of the fluid, we're using Eulerian domains, and those are relying on equations of state for the fluid. And in the case of the simulations that we're using what is defined in the computer software abacus as a USUP fluid type model. So when you create a simulation like that, as I mentioned, we have Eulerian and Lagrangian meshes interacting with each other, one simulating the behavior of the fluid, the other one simulating the behavior of the solid, and everything is responding to the interaction between the two. As the fluid impacts on the solid deforms, and that affects or informs the way in which the fluid behaves around the solid. So these models are computationally very, very expensive. It takes a lot of resources to do a simulation. Our early stage in the project was to develop some simpler models to improve the way in which we simulate the hydrodynamic part. So we were concerned about being able to simulate waves correctly, simulate their velocity, and also since we're only simulating a small fraction of what is a very large domain, we have to worry about waves being reflected or not being reflected more accurately. So we need to understand how to model inlets and outlets properly. In addition to modeling the wave, a big part of this component, as you may surmise, is logical, is the fact that you have to simulate the impact of the wave properly. Which means we need to be able to have confidence that the forces that we calculate during impact are forces that are estimated accurately. This type of simulation we've been performing in the computer program Abacus, and so the way that we do, we start, this is a simulation, a typical simulation, just a fluid. There is no solid in this one. And so we model an entire Eulerian domain. Some of it is filled with water. Some of it we leave as void. And then we applied velocity boundary conditions to form a wave, and zero pressure on the other end to provide for the possibility of an outlet. So this shows the simulation of a wave, and as you see, we're generating a velocity field on the left end in that in a sinusoidal fashion, and that forms a wave that propagates from left to right on the Eulerian domain. And so our goal is to be very confident that when we set boundary conditions here, and the amplitude and the frequency of that boundary condition, that we generate waves that have a certain amplitude and boundary condition, because that would be one of the engineering design parameters that we would want to study. Then we migrate to models where we have a solid embedded in it. This is just a very simple model with a piece of an eye girder. So this simulation shows the fluid and the velocity field within the fluid, and interesting shows the interaction between the fluid and the structure, and the way that the structure affects the behavior of the fluid. So it seems very natural flow. We were quite happy to see the way that the fluid reacted when it went around the girder. The other part of this is we're also concerned about the solid is doing. So if we forget about the fluid for a minute and we focus on the solid, this simulation or this video shows the calculated stresses on the girder. And so this implies that the fluid is doing its part and that the solid is also observing some deformation as a result of the impact of the fluid on it. So we can generate straight contours as the wave progresses through the fluid. Okay, so once we have these simple models, then we set on to use larger calibrations. There are two experiments that I'm going to be talking about today. One that were performed on the Oregon State flume. One was an experiment simulating the tsunami impact of a tsunami wave on a timber wall. And the second one, I think more relevant, is a bridge that had been modeled many different times, so is a great platform to develop confidence on this type of modeling. Is a bridge that on I-10 over Escambia Bay that was damaged during Katrina. So for the timber wall boundary, this is the Eulerian domain, the water level, and the boundary conditions as we specified, trying to simulate or replicate what was the geometry of the flume. And as we generate the waves, this is velocity of 2.2. The wave comes up and then impacts on the wall, as you can see it over there. The wall is made out of timber. It's a fairly flexible wall. And throughout this experiment, there were measurements that monitored the height of the fluid, the velocity of the fluid, and also the forces and deformations in the wall were monitored. So it gave us a lot of different places where we could track the goodness of fit of our simulation. So for example, this is one of the locations where the researchers measured the wave height. And we see in this case, in this graph, comparison between measured and calculated water elevation versus time. The other point that they, there are several points in which we check. Again, one of our concerns or major concerns is being able to generate those impact forces properly. And so at the wall, there was a location where they monitored displacement. And again, we show comparison between the test in orange and the model in green that tracks the displacement of a point in the center of the wall near the bottom. And we were able to obtain pretty decent matches. And then, of course, the one that we had the most concern about was being able to simulate the reaction forces on the timber wall as the wave impacted the wall. And we were able to obtain a relatively good match between the forces that were calculated and the forces that were measured. In here, we see a little bit of that effect that I was mentioning before, where the wave comes, it impacts on the timber structure and generates a very high amount of force, which then subsides and gives way to a more hydrostatic type force, a more constant type force. So the effect of that on connections of this peak, on connections and on the dynamic response of the structure is an important question that we need to learn a lot about. The second model that we studied was the bridge on Escambia Bay. This is so folks in Oregon State took the plans from Florida DOT and they reproduced it at a scale of approximately 1 to 5 in their flume. This is an image of the model that was tested in the flume. Now we see the limitations. Even though they did some things to simulate the flexibility of the substructure, that becomes a matter of question and a matter of research. So this is what the computer model looks like. We model a segment of bridge. In this case, in the results that I'm going to present quickly today, we did on fixed foundation, so it neglects the deformation or the ability of the substructure to deform. And so this image shows the simulation. We generate a wave in the same way that we've been describing. That wave impacts the bridge and generate forces on the bridge, and then we calculate the reaction forces that are generated as a result of the wave impact. So this shows the amplitude of the wave in I'm running short on time. As a matter of fact, I'm down to my last slide. What's important from this slide is to mention that those are representative of once you account for scale factors of what you might have expected in Hurricane Katrina. And so we have this very same type of behavior where the wave impacts the bridge that drives very large increase in force when the moment of impact, very large force that over a very short duration, and then the effects subside over time. And so we can calculate reaction forces either in the vertical direction or the horizontal direction, or we can calculate the resultant, and that accounts not only for vertical, horizontal, or uplift. These numbers that you see here normalized to bridge weight, they're extremely high. And so we think that part of the reasoning is we're not properly accounting for the flexibility of the substructure in this problem, and that's certainly one of the questions that we hope to answer with our ongoing research. So again, what's the future for us is to begin to understand a little bit better how these models work and how to develop more confidence in the way they work, and then we intend to use them to study different types of support conditions of connections and what type of damage one might expect to happen to those connections as a result of hurricane type excitation. So I'm going to leave my presentation here. I think I actually went 2 minutes over, so I'm going to pass the baton back to Chris.
Sounds great. And I'll go straight to the next presentation, which actually has two speakers, and they're both from the Colorado DOT, Dr. Oana Ford and also Miss Lizzie Kemp Herrera. Dr. Ford is an economist and risk and resilient lead at the Colorado DOT. Dr. Ford has been providing economic analysis support for CDOT for the past 2 years. She has been a resource for benefit cost analyses, economic impact analyses, project selection methods, and mobility data analysis. She works in Denver, Colorado in the multimodal planning branch in the Division of Transportation Development at CDOT. And for Ms. Lizzie Kemp Herrera, she holds a master's degree in city planning from UC Berkeley and has held various transportation planning, funding, and policy positions in California and Colorado for over 25 years. Currently, she manages CDOT's Planning and Program Management Group in the Denver metro area. She was the co-manager of the I-70 Risk and Resiliency pilot project, which was completed in early 2018.
Okay, so thank you, Chris, for the introduction. I'm going to start. This is Lizzie Kemp Herrera, and I'm going to start with the first part of the presentation, and Dr. Oana Ford will finish up. So our presentation is about a pilot project that we initiated, probably a good year and a half ago, to look at risk and resiliency planning on the I-70 corridor. I-70 is about a 450-mile-long corridor that crosses the entire state of Colorado from Kansas to Utah. As Chris mentioned, the study was completed earlier this year. So next slide. In 1976 and again in 2013, we had some really devastating floods here in Colorado. And what you're seeing on the screen is two pictures of the very same area, and the floods destroyed that roadway in both instances. So one of the questions that we've had is, what can we do now in advance of some of these events to make sure that when we are building structures, that we're building them to be able to withstand some of these sorts of events that we see. As I mentioned, where there's significant roadway damage happened in the 2013 flood, about $700 million worth of damage and roadway repairs. And when they were rebuilding from that, they were working with FHWA on the Emergency Relief Program, which has some rules about how you can rebuild. And typically, they like you to rebuild in kind. That is, replace what was there beforehand. We worked with FHWA, our division office, to figure out how we could demonstrate that there was a benefit cost to building back better, with the idea that we saw very similar damage to these facilities from the 1976 floods and the 2013 floods. Isn't there something that we can do now to build that back better, so that we don't have that sort of damage in the future, and then also demonstrate that there's an economic, it's a benefit cost. We're spending money now in order to not have to spend money in the future. So next slide. So the purpose of the study was to say, what can we do now to avoid some of these things in the future? So for Colorado, that means a lot of our physical events are floods or rockfall. So you see some of the types of damage that we've seen in our system from past events. And so what can we do now to avoid that in the future? Next slide. So on the next slide, it talks a little bit about what that pilot is an analysis of potential risk and system resilience of I-70, again, across the entire state, from Kansas to Utah, 450 miles. And so instead of looking at a reactive response to when these events hit, and then how do we build back better, the purpose of the pilot was to look proactively at what are the optimal investments that we can make now on our system in advance of those future events to improve our resilience. And it builds off of what's called the RAMCAP process, which is an ASME standard that was developed after the 9/11 terrorist attacks to look at all sorts of hazards and what kind of risk and resilience measures could be put in place. RAMCAP stands for Risk Analysis and Management for Critical Asset Protection, and it's a 7-step process. Next slide, please. That process, here are the 7 steps in it. I'm not going to go through each of them, but it lays out a framework by which anyone can really use this methodology to analyze what the dollar cost risk is of various types of threats. Next slide, please. In layman's terms, this is the way that I like to describe what RAMCAP did, is that we looked at what were CDOT's assets, so what's the location, value, condition, and criticality of all of those assets. What are the physical threats that are relevant to those assets? What's their likelihood and the location that they might happen? What impact would those threats have to our system? Looking at what are the consequences, how vulnerable are our bridge structures and roadways to those sorts of events? And then finally, what are the optimal investments that we can make now to improve resiliency in advance of future events? Next slide. So a couple of key concepts. In the RAMCAP model, risk is defined as the probability of the threat, how vulnerable our assets are to that threat, and then the consequences. So it gives us an annualized dollar cost risk associated with that with different threat asset pairs. Risk is the potential cost of losses to CDOT assets, both as an owner and to our users. And then resilience is the ability to remain functional even in the presence of those risks. Next slide. One of the really nice things about the RAMCAP model is that it is an all hazards methodology. So it looks at all different types of hazards, not just focusing on one. So we looked at all of the threats that you see on the left-hand column there, and looked at all of the asset classes that are shown on the right, and really looked at threat asset pairs and what those potential risks are. Next slide. One of the things that the RAMCAP methodology does is to look at what are the most critical assets on our system, and by critical, it's critical in terms of resiliency. The way that I like to describe that is which assets, if they were taken out, if they were destroyed, would most have the largest operational impact on our system. And we wanted to refine that in a way that made sense socially, economically, and environmentally. So this was the model we used to identify which assets are most critical. We looked at usage, which roadways were carrying the most traffic, economic impact in terms of how much freight was being transported on those on those roadways and what's the value of those roadways to our tourist industry. Social impact we measured by the Social Vulnerability Index, which is a multi-variable index that shows how vulnerable a population is to, how difficult it is for a population to recover from various events. So it looks at a lot of socioeconomic characteristics of a population. And then system impact. So are there redundant routes that would allow, if a certain roadway was taken out, that there were alternate routes that could serve as a detour. And if there weren't, then maybe that's more critical asset. So next slide shows the map that resulted from that criticality. So you'll see that we do have a number of areas that are more critical in the state than others in terms of our assets, which we thought was a good indicator that we were seeing a number of a good model for which assets are most critical. Next slide. So then we did the consequence analysis, which was what happens during the worst reasonable event. What are the consequences? And so we looked at, for instance, flood and bridge. We looked at rockfall and roadway prism. And what's calculated from that is both the owner cost, which is the asset replacement cost, and then the user cost, which is largely driven by the value of time as a result of delay or detour. And so that's what the RAMCAP model delivers for us, is an annualized risk, both owner cost and user cost, that would happen with the worst reasonable event on all of our facilities. So with that, I'm going to turn it over to Oana. And she can talk to you a little bit about the results.
So I'm going to walk you through the results of the pilot and also how we were able to use these results in economic analysis to determine which mitigation alternative should be chosen in some of these high-threat, high-risk locations. So let's go to the next slide. So the results can be sliced and diced in many ways. So right there at the top, you can see the whole of entire corridor from the Kansas to the Utah border and going through Denver. And we were able to segment that corridor into different segments. They're named from A through M. The way we segmented the corridor was just based on logical entry and exit points off of the road. And this slide represents the total risk that we calculated by these corridor segments that we partitioned the road by. So as you can see, the segment B has the highest risk valuation, about 85 million off the entire corridor. That is also a highly critical corridor. If you look at the bottom, the red and the yellow shows the criticality of the segment. It's what Lizzie just talked about, that criticality map. So not only that segment B has the highest risk valuation, but it's also a highly critical segment. So that segment in particular goes from Rifle to Loma in Colorado. And what's driving that risk valuation is really a flood risk because the Colorado River just goes along the road throughout that whole stretch of that segment. Segment C is the second highest risk valuation coming out of the pilot. And that segment from Rifle to Walcott contains Glenwood Canyon, which is one of our most beautiful but also sensitive areas along the corridor. It's a canyon that follows the Colorado River, and the roadway in that canyon is made up by PTCS, so post-tension concrete slabs. Those are quite expensive to build with. So any rockfall events that happen in that canyon that damage those PTCS concrete slabs will be quite expensive to fix for CDOT. Can we go to the next slide? So this shows another view of the data. This is the annual risk by threat. So this shows the user risk and also the owner risk. The user risk is in blue, and it's the risk to our users. It's the valuation of the risk to our users. So based on what Lizzie was saying, that's basically the value of time of taking lengthy detours and also the vehicle running costs for our users. The owner risk, that's in orange, and it's the risk to the owner of the asset, which is basically CDOT. So our risk is really composed by having to replace and repair that asset once an event happens. So we can see from this slide that the owner risk to CDOT is really the highest for rockfall. That's about 3.8 million. And that's, again, it's driven by the concrete slabs that the road is made out of in Glenwood Canyon. Glenwood Canyon has a high risk of rockfall, and we've actually had a rockfall event there recently that closed I-70 for about a week. In terms of the user risk, we can see that their user risk is highest for flooding. So the risk to our users it really comes from flooding, then rockfall, then avalanche on the corridor. Let's move on to the next slide. So this is, again, another view of the data. So this shows those segments that we partitioned the corridor in, and it shows the user risk and the owner risk. We can see that segment B, which is, again, that low much rifle segment, has the highest user risk, and that's probably because of flooding. Again, the Colorado River is right next to the road in that section. If you look at segment C, that bears the highest risk for owner risk. That's the risk to CDOT, and that's Glenwood Canyon. Let's move on to the next slide. So this is another way to look at the data. So this shows basically one segment. So segment C, it's circled in red at the bottom, and it just tells you that really on that segment, rockfall is the highest risk, followed by flood, followed by bridge vehicle strikes, and then it also gives you a total risk for that segment. So there's multiple ways to look at the data depending on really what you're looking for and what you want to do with it. Let's move on to the next slide. So what we did next, now that we have risk valuations for all of the assets and all of the threats and all of the locations that came up as problematic and risky in the pilot, now that we have those valuations, how do we really use them? What do we do with them? So we took a deeper dive at 5 specific sites, and we try to incorporate this risk valuation in benefit cost analysis of different mitigation alternatives at each site. So we chose a variety of threats and assets. So we have a flood and bridge example, rockfall and PTCS, which is those concrete slabs that I was talking about. That's one of the examples. We have a flood and bridge approach, a flood and minor culvert, and the landslide and roadway example. And I'm not going to go through all of these, but I'm going to go and do a deep dive into one of them. But one thing that I do want to mention here is that we've seen, even from the federal government, we've seen a push to incorporate resilience and quantifying resilience to incorporate it into benefit costs. If any of the DOTs that are online have applied for any infra or build grants, and if you've read those benefit cost guidelines from the US DOT, they've just added for those, for this go around this year, they've just added a chapter on resilience and how it can be incorporated into benefit costs, and how if you do have these valuations, you should really be incorporating them. So these, I'm going to go over an example of how we can do that. And that example is number 2, so the rockfall and the PTCS example. Chris, if you want to move the slides along. Thank you. This example is from Glenwood Canyon. I've mentioned that before. It's on I-70, and it runs along the Colorado River. So if you look at the picture on the left, it shows the road with the Colorado River on the left-hand side, and then the steep canyon walls on the right-hand side. The area that we investigated, if you look at the picture to the right, really shows the two directions, westbound and eastbound, the two directions of traffic, and then it shows the rock sheds, the slides that could happen above those locations. This particular stretch of the road carries about 26,000 vehicles a day with about 13% truck traffic. So it's really quite an important area for the economic vitality of our state. So when we looked at this location, we found out that there are some rock mitigation measures in place already. So there are 5 2,000 kilojoule fences, rock fences, at this location currently. And with those rock fences in place, we were able to model in a software, in a geohazard software, we were able to model the impacts of a rock slide, and we were able to quantify the annualized risk as a total, so owner and user risk, to 1.2 million at that specific site. So next, if you want to move on to the next slide. So what we did next was we went to our CDOT experts and tried to figure out what mitigation measures we can put in place at this site to make it more resilient. So there were 2 options that were suggested. Option 1 was to replace the existing 5 fences that were 2,000 kilojoules fences with 5,000 kilojoule fences. And the cost of mitigation for the entire site, so replacing all 5 fences, is 1.4 million. The second option suggested by CDOT experts was to, instead of replacing the fences, keep the fences that we have in place and really build a new 140 feet wall in addition to the fences on the site. So this second option came up to a cost of about $350,000 to build a wall. Let's move on to the next slide, which I believe is my last. So we were able to model both of these options in our software and see what the consequences would be if we had a rockfall event with both of these mitigation options in place. So what we can see is that the annualized owner risk and user risk, as well as the total risk, they all decrease under both options. Option 1 really gives you a steeper decrease in that risk, so you're really buying down a lot more of the risk by replacing those 5 fences with 5 fences that are stronger. But when you look at the benefit cost, so that's the last column in that table, if you look at the benefit cost, for option 1, the benefit cost is 2.7, and for option 2, the benefit cost is 21.2. So because of the higher cost for option 1, perhaps option 2 is better. So I should really say that anything above 1 is really worth considering, with a benefit cost ratio of above 1 is worth considering by a public agency. But you do have to take into account the reduction in risk, but also the cost of the mitigation measures. So again, this is one way that you can incorporate risk valuations and resilience into a benefit cost analysis. And I believe this is my last slide. So thank you for listening.
Perfect. No, thank you very much. But we are running a little bit behind schedule, so I'm just going to quickly introduce our last speaker, Mr. Rob Kafalenos. Mr. Kafalenos has been Environmental Protection Specialist in the Office of Natural Environment at the Federal Highway Administration since 2001. He works primarily on policy development and research focused on adaptation and resilience, including links to asset management and project-level engineering. Rob's work includes managing the ongoing FHWA Asset Management and Resilience Pilot Program in cooperation with Steve Gage, and development of the synthesis of approaches for addressing resilience in project development in 2017, which summarizes lessons learned in project-level adaptation based on a range of analyses conducted across the U.S. He holds a master's degree in environmental management from Duke University.
Great. So today I'm going to talk, broadly speaking, about Federal Highway's approaches for addressing resilience to extreme weather events. So now my slides are not advancing. Oh, there they go. Okay. So this is basically what I'm going to talk about. I'll talk about some of our approaches, talk about some of our ongoing pilot projects, and then I'll give a brief summary of some of the resources that we have. So first of all, what is resilience? It's a term we use a lot without really defining it. I would just say that resilience in some respects is a state of being. It's the ability to anticipate or prepare for or adapt to some kind of threat. Adaptation refers to activities that we take to make ourselves more resilient. And these pictures at the bottom are examples that are now somewhat dated, but that refer to different places that were not resilient to floods, to fires across the country and in both coasts. So these are some more recent pictures, but by recent I really mean last year. These are pictures that show why resilience is important. These are areas in Texas and Puerto Rico that were affected by Hurricanes Harvey and Hurricanes Maria. So it really becomes clear during emergencies the importance of resilience. But in addition to thinking about current threats, we also need to consider long-term change. So while we think about resilience as it relates to current conditions, we also need to think about how those conditions will change in the future. If we build a bridge today, and I think particularly our second speaker spoke a lot about what can happen to bridges along the Gulf Coast region. If we go in now and try to replace a bridge, we need to think about what that environment will be, 75 years from now. Obviously, we can't predict what it is, but we can think about what it could be, giving an understanding about how the environment's changing. So in a nutshell, assets need to last, and we need to build them to last. So at Federal Highways, we try to focus on resilience in basically 3 different categories. We think about resilience at the planning scale. So at the state and metropolitan planning scale, we focus on project level issues and also operations and maintenance. So I'll speak a bit about mostly the planning scale and the project level and project development scales. So the Department of Transportation in its strategic plan released earlier this year highlighted several things that are considered very important by the department. So one of them is thinking about that the DOT would commit to increased effectiveness to ensure that infrastructure is resilient to extreme weather. So that means trying to make sure that we build infrastructure and consider how we build it through asset management and project development to make it last. Federal Highways issued an order 4 years ago committing the agency to focus on resilience to extreme weather events going forward. We've also tried to deal with this through eligible notes on what is eligible for funding and also through the EER program. More recently than some of those, we have the risk-based asset management regulation that's now in effect. So at this point, asset management plans must address risks associated with current and future environmental conditions. Assets that require repeated repair under the Section 667. There's an analysis process that states are going through right now to understand where assets have needed to be repeatedly repaired over the last 2 decades. Also, metropolitan transportation organizations are supposed to, in their long-range transportation plans, are also needing to analyze projects that can help reduce vulnerability of their transportation systems. So that's just a broad overview of some of the policy and regulations that affect us and where we're headed. Next, I wanted to talk a bit about some of our pilot programs. So this slide summarizes most of the pilot programs that we've done. And at Federal Highways, we've tried to work with and support a range of states across the country to, at first, just understand the vulnerabilities. Those are those states and MPOs that are highlighted in orange. That was about 8 years ago, where we worked with Washington State, Hawaii, Virginia, New Jersey, and others to kind of help them and learn from them to develop processes for understanding what assets could be vulnerable going forward. We also had programs that went the next step to where states were going in to understand not just what was vulnerable, but how to improve those assets to make them more resilient in the future. And then we have two other programs that are about halfway through that I'll talk briefly about next. So the first up is the nature-based resilience pilot program. So nature-based features is another way to talk about, we use that term, we use the term green infrastructure. That's basically referring to man-made features that are done to work with or to mimic natural processes. So this particular pilot program focuses on coastal areas, and many of the pilots are investigating things like supplementing marshes, dunes, beach nourishment, supporting wetlands and rock revetments. One of the reasons that we're interested in nature-based features is that they can oftentimes be cheaper than, say, putting in something like a seawall. They can also be more effective in dealing with sea level rise, at least in the near term. There can also be co-benefits for the habitat and for fisheries and for recreation. And one of the things that we try to talk about and that we support is the idea of an integrated approach that uses some mixture of structural options along with nature-based features and also policy features that can help protect assets. So currently, there is an ongoing pilot program. The 5 pilots, I think, are just about done. Many of these are already posted on the Federal Highways website. So it's Oregon, Maine and New Hampshire, Mississippi, Delaware, and then one that involved New Jersey and the Army Corps of Engineers. There's a white paper that's being put together as well as an implementation guide. The implementation guide will kind of summarize options and ideas about how to use nature-based features going forward, and that will come out next year. The other ongoing pilot program is the asset management and resilience pilots. This is a project that we're running in our Office of Natural Environment in combination with the Asset Management Office. We have 6 states involved listed here. You'll see some are coastal, some are not coastal, like Kentucky is not coastal. They're concerned with things like precipitation-related flooding. Massachusetts is also looking into things related to precipitation-based flooding in riverine environments. Anyway, these pilots are about halfway through. We expect to have these done by the end of the year. And as part of that, we'll also be developing a guidebook that will pull together lessons learned from these 6 pilots and then spread this out to the rest of the states. One of the things, I think one of the earlier speakers also focused on this. One of the things we're finding is in all our pilot programs, but I'd say particularly in asset management, is just this need to break down silos, where we're trying to get planners, asset managers, and environmental people, as well as engineers, to work together who may come from different perspectives about the environment and how to deal with it. So just in a nutshell, what is asset management? To some people, it may be somewhat of a new term. Asset management is really a systematic process of operating, maintaining, and improving assets to identify a structured sequence of activities to achieve and sustain a desired state of good repair over the life cycle of the asset at minimum practical cost. So asset management is really one of the key features of it, is to think about assets over their entire life cycle, find the best ways to either maintain or improve the quality of those assets and the services they provide at minimum cost. And the asset management rule talks about the contents of what goes into an asset management plan. And I won't read them all here, but there are 7 different chapters or sections that go into asset management plans. And the 2 that are related to resilience most are things related to life cycle planning and risk management analysis. So when we think about risk management and life cycle planning, resilience is one of the key factors to consider. So within the plan, states are putting the risk management plan that they are put together is intended to identify the risks that are associated with current but also future environmental conditions, including extreme weather events. And then the life cycle planning part, it should also include a range of factors that could affect the whole life cost of assets, including threats posed by those risks. So again, life cycle planning is considering investment needs over the service lives of those assets, which could be 50 years, could be 75 years for bridges. And in considering what that logical sequence of interventions is to maintain those assets in a state of good repair at least cost, that can be boiled down to some extent to these 10-year financial plans that are also at the heart of the asset management planning process. So I just want to mention a couple places that are already doing this to some extent. There's the LA County Metro in Los Angeles, which deals with both transit assets and highway assets. They've already started to integrate climate risk into existing asset management systems. They've included this new data fields within their asset management systems to kind of store that information. And also they developed guidelines for assessing risks to those assets. And MARTA in Atlanta has also done similar things. So there is one other pilot program that I'm not really going to say much about. It just got started a few months ago. I think there are 10 or 11 pilots at this point, and they're basically doing 3 different things. There's, I think, 1 or 2 pilots that are working to deploy a resilient solution and monitor it over the long term. So that will really go past 2020. That Massachusetts is one of those. There are also several pilots that are working to integrate resilience and durability into their general agency practices and policies. And then there's a third group that is doing something similar to our previous pilots, where they're using existing tools that either they've developed or Federal Highways has developed to assess vulnerability and risk, and then also in some cases to develop options for protecting individual assets for the transportation system in their states. So this next slide summarizes pretty close to 12 years of work at Federal Highways focused on resilience. I'm not going to talk about each of these individually. We'll just talk about a few of them. But some of these projects and resources that have been developed for states and MPOs to use focus on assessing vulnerability kind of at the systems level, also at the project level. Some focus on dealing with engineering, pulling resilience into consideration of asset engineering and development. There are a few tools that we've developed to help areas understand how to conduct vulnerability assessments and how to get information on future environmental conditions. And there's also been some work on operations and maintenance. So I just want to talk about a couple of these. The first, for people who may be somewhat newer to vulnerability, the first place to start for at least Federal Highways tools and processes is the Vulnerability Assessment and Adaptation Framework. This is the 3rd edition. It came out at the beginning of this year. It really provides a good starting point. It provides an in-depth structured process for conducting vulnerability assessments, both at the system scale and the project scale. It includes a lot of information and lessons learned from our state and MPO partners, and highlights some best practices that we've seen around the country for assessing vulnerability and adapting bridges or tunnels or roads to make them more resilient in the future. It also includes lots of links to resources and tools that have been developed not just by us, but by others as well. So this process is really, it's what we would consider kind of a logical framework, where it has the user start by, whether it's a state or an MPO or others, people sitting down together to figure out what it is they actually want to do in the study, what assets they want to focus on, and how to get the information both on the assets and on the environmental information, both today's environment and the future environment. Then it walks through and gives some examples and ideas about how to actually do the vulnerability assessment, which there's several different forms of this. One of them is an indicator-based kind of desk review process. Another is a stakeholder input process, and also at the project level, we have some tools related to engineering informed assessments that are discussed both in the framework and in a separate study that I'll say a few things about. But once a state or an MPO has put together information and assessed the vulnerability, then part of the real work is to decide what to do about it and how. And I think the last speaker spoke very articulately about economic analysis and how to use economic analysis tools to weigh different adaptation options, both considering the benefits and the costs. That's one thing that's very important to think about. But there are all sorts of other decisions that also can be made with this information, both at the planning level and at the project level and other phases of transportation. So the framework highlights a few individual tools, and I just wanted to highlight a couple of them a little bit more. We have two, or I should say our Office of Bridges and Structures and the Office of Infrastructure has put out 2 hydraulic engineering manuals. HEC 17 is the first one that it really focuses on understanding the riverine environment and understanding how future changes in precipitation can lead to changes in flooding. That was put out about a little over 2 years ago. A similar document was completed in 2014, but it focused on coastal areas. Both these documents provide information and understanding about our current understanding about whether it's precipitation or coastal issues, how things are changing. It provides different sort of a phase level of different levels of analysis to walks the user through how to do analyses about what future precipitation could be or what future inundation levels could be in these two documents. So the second one that focuses on coastal issues is currently being updated. Among other things, it will include information pulled from the green infrastructure work. And I think the last thing I really wanted to highlight is this synthesis of approaches for addressing resilience in project development. This is really the study that, and again, this was put together by both our engineering office and our environmental office. And the goal was really to summarize some of the information that we've learned and our state partners have learned, looking at understanding vulnerability at the project level and coming up with engineering solutions to make those assets more resilient going forward. It identifies lessons learned from all the different projects. It discusses the kinds of vulnerabilities to future situations and also adaptation strategies. And these are all organized based on the sub-bullets here, whether it's coastal or riverine, geotech, pavement and soils issues, and then also mechanical and electrical systems. Some of the work on the electrical systems is tied to some of the bridges in the area affected by Hurricane Sandy. And this next map basically shows where a lot of these engineering assessments have been done. Some of them were done in the Mobile area as part of the Gulf Coast 2 project, which is a multimodal transportation resilience project, and the Hurricane Sandy project in the greater New York City area. But then also a lot of these adaptation pilots that have been conducted by the states, whether it's in California or Washington State or Iowa or very many places across the country. And in this, we really tried to pull information together from multiple asset types. So whether it's bridges or culverts or tunnels or highways, and also very different, distinct environmental conditions. So I think I'll stop there. Thank you very much.
Perfect. Thank you very much, Rob. I propose to have a 10-minute Q&A session, and we can start with the Q&A box. There's one question left. I do appreciate all the speakers for answering those questions. So let's start with this first question, and then I'll ask the attendees if they would like to answer a question live. So I'll just read this first question out. It's actually for you, Rob. Pong Wu asks, is Louisiana in the pilot assessment management and resilience plan?
You think it's Louisiana? No. So Louisiana, I should say the asset management rule, it applies to all state DOTs. But for the asset management pilot program, no, Louisiana is not part of it. It's just 6 states. But ideally, the results from our pilot program will help inform Louisiana going forward.
Perfect. There's already a question on the Q&A box from Steve Neary. So it's basically for the Colorado, the CDOT presenters, and he asks how did you value time? How you quantify time?
Hey Steve, this is Oana Ford. I don't remember exactly what the value is, but it's basically there's lots of studies out there trying to come up with a value of time, and the US DOT has their own value that they suggest DOTs use. I'm trying to remember what ours was, and I can't right now, but it's basically a lot of research and just putting a value on people's time.
Oana, this is Lizzie. That my recollection is that we use the FHWA approved value of time.
Yep. Yeah. So you can look that up online, FHWA or USDOT value of time, and you can find out how. I think they basically did a research project and looked at all the research papers that addressed this, and came up with a value that they were confident in letting people use.
Perfect. I do have a question. actually for both Rob and Lizzie and Dr. Forrest, is that I-70 CDOT project just something that CDOT did, or is that also related to like one of the FHWA pilot programs?
So I can try to answer that. It's not actually one of the FHWA pilot programs. However, we were very strongly encouraged and supported by our FHWA division office in doing the pilot and part of that came from, we used the RAMCAP process to do our benefit cost justification for building some betterments as a result of when we rebuilt after the 2013 floods. And one of FHWA's desires when they saw that we were using that model was to say, that's fine, we'll work with you to do some of the betterments that make economic sense right now, but we'd like you to start using that in a proactive way so that it's not just as a matter of ER reconstruction funds, but that we actually got a handle on what some of the resilient things are that we could do ahead of those events. So it came out of a lot of cooperation with FHWA and encouragement by them to go down that path.
Yeah, and this is Rob. I would just say there's not a direct link from our office at least, but it's one of the projects that we followed and have been really interested in. I still remember when one of the consultants came here and talked about the project maybe 2 years ago, and then certainly there have been discussions over the years, so it's really good to see. One of the really interesting things, and I've already said this probably, is that some of the way the economic analysis is done is really something that is useful to see, and I think it has there are a lot of people interested in that. You know, how people go through and consider costs and benefits and consider things like avoided damage as benefits is something that's somewhat newer, I'd say, for this field, but I'll defer to Oana and Lizzie on that. But that's something that we certainly think is a really useful thing to do. There's NCHRP work that's coming out on that in the next few months, and there's also some of our Gulf Coast 2 work. Some of our work in Mobile tied to our TICR project also try to deal with certain things like that for benefit costs.
This is Lizzie. I have a question for Rob. You mentioned that in one of the newer series of the pilot efforts that you've got some DOTs that are looking at organizationally how to incorporate results or some of this information into day-to-day business. Which states are doing that type of work?
I need to look at the map just a second. So in terms of, that's a good question. I don't really have a good answer. I'd have to go back and look at the individual proposals.
And that's all right. I guess maybe we can do that offline. We're currently trying to get that same sort of an effort done, and so it might be useful to see what others are doing.
I would say I think that most of them are doing what I would call this second category, which is basically trying to use existing resources to understand vulnerabilities and look at adaptation options, whether it's the project or systems level. There are a few that are doing this sort of working more from the perspective of investigating their own agency practices and trying to work resilience into those processes. But yeah, if you just send me an email or give me a call, I can find that information for you.
Awesome, thanks.
Sure.
I do want to sincerely thank each of the presenters. Honestly, that was quite a unique topic that came together. I think it came together really well and really beautifully, actually. So again, thank you very much to the 5 presenters and to the attendees. Again, this is being recorded and the video will be on our website along with the compiling of these slides as well. And feel free to reach out to me if you have any questions. I think the presenters also provided some contact information, so also feel free to reach out to them to continue, this conversation. But again, thank you very much for attending, and have a great rest of the day.